Okay, that is f. So let's just put it over there, take the logarithm, put it over there, and take the derivative. Sorry, there is another mistake I made. You see here, when I make this change of variable, dz is equal to I dy, so there's no I over here. And remember, x0 depends on omega r's through this equation. You see, if you look at f, there is no explicit omega r0 dependence, but it depends on omega r0 through x0. That's the only dependence. So logarithm of f will be n times g of x0 minus 1 over 2 logarithm of g double prime of x0 plus other terms independent of x0. And hence omega r. So the derivative with respect to omega r0 will be n times derivative of g prime of x0 times derivative of omega r0, derivative of x0 with respect to omega r0, minus 1 over 2 third derivative of x0 times divided by the second derivative with respect to x0, derivative of x0 again with respect to omega r0. Well, the first term is 0 by definition of x0. So I need to calculate this derivative. And that is where I use the advantage of being the instructor. I will not do that derivatives. I will leave it to you. If you do the remaining computation, there are more details in the book. You will find that the average value of nr over n is actually equal to e to power minus beta er over q, which is nothing but nr star over n. So we have this ensemble. We are trying to extract some information from our ensemble. So there are two things we can look for. We can ask for what is the most probable distribution of microstates in my ensemble. Or we can look at what is the average distribution of microstates in my ensemble. And imagine I can have infinitely many different ensembles, each being equally probable. Although this ensemble is equally probable, when I look at the number distribution of microstates, the most probable value and the average value, they turn out to be equal. And in fact, you see, the average is the most probable value plus some other corrections from other distributions which are less probable. But this also tells me that there are no such contributions. So almost the only contribution comes from the most probable distribution. Well, the next thing you can do is, what is this number? You see, which we define as the average of the square of this average of the square of nr minus the average of nr squared divided by average value of nr. Well, you see, we calculated nr average by taking the derivative with respect to omega r of omega of nr. The second derivative, the logarithm of So we had defined this, yes, f. Now we could do this because since we introduced these numbers omega r to the power nr, well, nr times omega r to the nr is nothing but omega r times the derivative with respect to omega r of omega r to the power nr. Well, I can do this twice. This will be equal to 1 over f of omega r, whatever that function is, omega r times derivative with respect to omega r times derivative with respect to omega r of f of omega r. Due to this identity over here, the action of omega r times the derivative with respect to omega r, it just brings down a factor nr. In fact, that is why I mean, since we are setting omega r to 1 eventually, multiplying by omega r doesn't really make any difference here, but here it makes a difference because I'm taking the derivative of this omega r before setting it to 1. That is why I'm multiplying with omega r since the beginning. And in fact, you can just go ahead and show that delta nr is actually equal to of the logarithm of f of omega r. You see, this term over there is not just the derivative of the logarithm. But, no, this is squared. Because there are two derivatives in between. You are taking the second derivative of your function and then dividing. If it was the first derivative, it was just the derivative of the logarithm. But since here you are first taking the second derivative and then dividing by the logarithm, divided by the function itself, that is not the second derivative of the logarithm. But if you subtract this term over there, what remains is the second derivative of the logarithm. Again, I'm skipping these steps. We have already determined our function f. We know its dependence on x0. You have to take all the derivatives. And this delta nr over nr turns out to be proportional to 1 over nr plus terms of the order of 1 over n. Now, what does this mean? When you set n goes to infinity, this goes to 0. But when you set n goes to infinity, all these nr's, they also go to 0. Because you see the nr over n, this is e to power minus beta er over the partition function. The right-hand side doesn't depend on n. So if you set n goes to infinity, so does the average values of, you see. Well, that kind of makes sense because just take a huge number of copies of your system. If there is one copy in a given microstate, if you double your copies, you will have 2. If you triple your copies, you will have 3. If you have infinitely many copies of the same system, you will have infinitely many copies in a given ensemble, in a given microstate, in your ensemble. But that means that this just goes to 0 as n goes to 0. So these numbers, although we are talking about the averages or the most probable, the probability of a fluctuation, a fractional fluctuation goes to 0.
How does the second term goes to 0 as probably n goes to 0?
This one.
Yes.
Because it's proportional to 1 over n with something that doesn't increase with n. I'm saying, oh, sorry, it goes to infinity. Sorry, not 0. I have infinitely many copies in my ensemble. Any questions? Well, this is something that you should do on your own once in your lifetime, at least until you start teaching. The steps, there are more steps in your book. I mean, I'm not doing anything other than what is also already discussed in the book. So let's give a 10-minute break here, and then we will continue.